We are deriving the governing equation that describes how temperature evolves in time due to heat conduction in a one-dimensional solid. Temperature is a scalar quantity that depends on position and time in this equation. The independent variables are space and time. For this problem, we will assume that it is both homogeneous and isotropic, and there's a constant thermal diffusivity as mentioned, and that heat transfer only moves in the x direction, since, of course, this is a one-dimensional slab. We will now begin by writing the energy accumulation equation, which is the rate of energy accumulated inside of a controlled volume, in this case a one-dimensional slab, is equal to the rate of heat conduction in minus the rate of heat conduction out. So that is our energy balancing equation. The rate of heat entering at the control volume at, let's say, position X is equal to the heat flux at position X multiplied by the area of the control volume. That is subtracted from the rate of heat leaving, which will be the heat flux at position X plus dx multiplied also by the area. Now that we've found the net rate of heat being added to a control volume via conduction, we can find the rate of energy accumulated. Energy accumulated or energy stored in a material depends on two factors, mass and temperature. That can be written out as the density of the material multiplied by the area at an infinitesimally small space, like a thin slice of a slab, times the specific heat capacity, because every single material stores heat differently, multiplied by the rate of change of temperature with respect to time. Looking at these two equations, we can first start out by canceling out the areas and rewriting the equation as density, heat capacity, rate of temperature. There we go. And you'll notice that this side of the equation can be rewritten as a derivative. Negative heat flux with respect to distance. And that will be set equal to our rate of energy accumulation. We can further simplify this equation into density multiplied by specific heat capacity, the rate of temperature with respect to time. There we go. And as you've noticed, we haven't used Fourier's law yet, so let's implement that. Heat flux is equal to the thermal conductivity, negative thermal conductivity, multiplied by the rate of change of temperature with respect to distance. If we substitute that into the equation, we will find that the negatives cancel out, and instead you get a second derivative. And now this tells us how the slope is changing throughout space. The final step is to divide both sides by density and heat capacity. Thermal conductivity divided by density and heat capacity is equal to thermal diffusivity. So our final equation, simplified, becomes thermal diffusivity multiplied by the second derivative of rate of change of temperature with respect to distance is equal to the rate of change of temperature with respect to time. This equation tells us something very important and very specific. The time rate of change of temperature at a point is proportional to the spatial curvature of the temperature field at that point. The proportionality constant, thermal diffusivity, has units of meters squared per second and sets the time scale at which the temperature disturbances smooth out. And that's the key takeaway. This is not a heat equation about heat. This is a temperature evolution equation that emerges from conservation of energy and constitutive law. We learned that the one-dimensional heat diffusion equation is equal to the one-dimensional heat diffusion equation is equal to the rate of change of temperature per unit time, which is equal to the thermal diffusivity multiplied by the rate of change of temperature over a distance, second derivative. From that, we can apply our method. To solve this equation numerically, we will draw our rod, and we will divide the rod into small, equally spatial segments. Now it'll be more equal than what I just drew. Call that delta x, where x is equally spatial segments. And that's going to be over equally spaced units of time. So delta t. We'll say that this is a timeline. Oh, that is not straight. This is a timeline. Yes, more straight. And we'll equally divide those as well. Each segment we'll label as I. So this is I plus 1, I plus 2, I plus 3, and each segment of time is n plus 1, n plus 2, n plus 3. Oh, that's not a 3. So for our temperature, we can say our temperature is based on our time, n, and our distance, I. This will be called our time step, and our I variable will be called our spatial node. The time derivative is approximated using a forward difference. So our rate of change of temperature per unit time is equal to our temperature at time n plus 1, so our time step plus 1, at the spatial node I minus our time step n, right, at the same spatial node, and that's over the change in time. The second spatial derivative is determined using a central difference. So our rate of change of temperature, second derivative, at a certain distance is equal to our temperature at time step n of I minus 1. So our spatial node minus 1 minus 2 multiplied by our time at the same time step at spatial node I plus our temperature at the same, once again, the same time step at our spatial node plus 1 over our changing distance x squared. Substituting these approximations back into our heat diffusion equation, our one-dimensional heat diffusion equation, we get this final equation. Let's do this quickly, not to waste your time. Minus, there we go, almost finished. And that is our rate of change of temperature per unit time multiplied by the second derivative of our rate of change of temperature per distance. Thermal diffusivity will also be a part of our equation because it's in our original one-dimensional heat diffusion equation. And if we want to find our temperature at the next time step to get our explicit finite difference equation, we need to do our time step plus 1, our temperature at that time step plus 1 at a spatial node I is equivalent to our temperature at first time step at our spatial node minus our thermal diffusivity multiplied by our change in temperature over our change in distance squared multiplied by this whole equation right here. Just the numerator. And that will get you our final explicit finite difference equation. Oh, my bad. I did a small miscalculation, and this is actually going to be plus our thermal diffusivity multiplied by this entire segment. The key parameter in this equation is this segment right here, our thermal diffusivity multiplied by our change in time over our change in distance squared. That will give us the key to whether or not it is stable. By it, I mean whether our numerical solution is stable. And our numerical solution could be a number of things. It just depends on what the parameters are for the equation that you're given. For this equation, our initial condition is going to be T of x of 0 is equal to 20 degrees Celsius. At distance x, at time equals to 0, our temperature is equivalent to 20 degrees Celsius. On our left end, we'll call this x is equivalent to 0, and our right end, x is equivalent to L. Our left end will have our temperature at 0 time T equivalent to 50 degrees Celsius, while our right end will have our temperature at distance L at time 0 is equivalent to, distance L time T, because we're not doing a specific time now, it's equivalent to 90 degrees Celsius. The rod is divided into equal spatial segments, poorly drawn by me, my bad. And as time progresses, as our time step increases, our finite or explicit finite difference equation will update the temperature. Let's go back to a key parameter. We'll call this R is equal to thermal diffusivity multiplied by the change in time over the change in distance squared. If R is less than or equal to 0.5, we know that our numerical solution is stable. The temperature gradually smooths out at each boundary along the rod. The temperature gradually smooths out at each boundary as the heat diffuses across the rod. But if this parameter is greater than 0.5, it is no longer stable. It is now unstable. The heat diffuses in oscillations and rapidly increases in magnitude versus a smooth increase. In a spreadsheet simulation, you can see this as a very large positive number or a very large negative number, which does not represent the actual physical heat transfer. So we've determined that our stability condition for our finite or explicit finite difference equation is our thermal diffusivity multiplied by our change in time over our change in distance squared has to be less than or equal to 0.5. So how do we determine that the stability condition is less than or equal to 0.5? Well, based on our initial conditions, our temperature at 0 is 50 degrees Celsius, and our temperature at length L is 90 degrees Celsius, and our temperature at time 0 is equal to 20 degrees Celsius, we can plug this into an Excel sheet and determine when our key parameter will tell us whether or not our numerical solution is stable. We have our Excel sheet right now, so let's make some assumptions. We will say that R is equivalent to 0.1. And we know that R has to be less than 1 in order for our numerical solution to be stable in some way, shape, or form. Our initial temperature is equivalent to 20 degrees. Our initial temperature on the left side of the rod is equivalent to 50 degrees, and on the right side of the rod, it is 90 degrees Celsius. At our time 0, we will go all the way until 600 just to have a number of values to work with. Let's keep going. We're at 500, almost 600. There we go. Beautiful. Oh, I forgot one thing. This has to be +1 each time, right? Because our time has to increase. Oops, simple mistakes. That happens, but we can always fix those. Happy little accidents. And we learn more after each accident. This will be our spatial node. And our spatial node -1, right? And that will be on the left side. And our left side starts at 50 degrees Celsius. And then so on from there, it's 20 degrees Celsius at time 0. Remember, at time 0. We'll just drag that along. We'll make some random guesstimate of, how many values we might need. We'll just go to X, and then our Y value will be 90 degrees Celsius because that's the right side of our rod. And so the left side of our rod is constantly 50 degrees Celsius, which means that we'll have to drag that all the way to 600 because no matter what time it is, that's 50 degrees Celsius. Let's just drag that to 603 so we get a nice even 600. Yeah, there we go. And again, our right side of our rod is consistently 90 degrees Celsius. Oh, don't go further. I think that's in line. Yeah, my eyes do not deceive me. This will be our node I, and this will be our node I +1. So we just arrived the explicit finite difference equation, right, from our one-dimensional heat diffusion equation. And we're going to plug that into the spreadsheet in order to determine at what point our key parameter, our R value, makes the temperature unstable. Our temperature at our spatial node I plus our R value, our key parameter, which we will change throughout the entire spreadsheet, but it's going to remain constant throughout the spreadsheet. So we want to put $signs in front of that number in order for it to remain constant, but we can change it later to determine at what point it makes the temperatures unstable. It's going to be multiplied by our temperature at our spatial node -1 minus 2 times, oh, yes, thank you for making that. Oh, she did not like that. Minus temperature at our spatial node I once again. Thank you. Our spatial node. Oh, so we have G2. Oh, we don't want G2, we want G3. Making a few errors here, and we want G3 again because that's once again our spatial node. Put that in parentheses. And then we have plus our temperature at the next distance, so H3. It's going to get us, oh, what did I do? Yes, please make that. All right, we got 23. So we're just going to drag that across all the spreadsheet, and that will get us an array of numbers. Do wrong. I see, I just don't have it set to the correct number of decimals. So we'll change that format cells. This is how you change it to the correct number of decimals. You can say you want it to be, let's just say 4 decimal places, right? Okay, and now just drag that all the way over. Perfect. And we can drag that all the way down as well. Drag that all the way over. There we go. Now we have a bunch of different numbers going on here, right? You just have a whole array of data. So scroll back up to the top and you will see degree, and that's how our heat is transferring across the rod over time, right? You see how it's very slowly, the rod is all 20 degrees, then, the middle becomes a little less cold and then a little less cold and a little less cold until our middle, the very middle of the rod starts temperature, right? It's very slow, right, compared to the left side and the right side of the rod, but it slowly gets there until it's at 56 degrees. As time increases, I'm sure it'll look a little different. Another thing we notice is that we can change our key parameter here, change it to 0.6. We'll notice very large spikes in temperature, right? Our whole entire spreadsheet just becomes numbers that we cannot understand. But when it's 0.5, perfectly fine, right? So that is how we are able to know that 0.5 is the moment in which we are stable. Anything less than or equal to 0.5 for a key parameter, our numerical solution is stable. But once it's slightly more than 0.5, things start to go awry. And that's how you can use Excel to determine this. So from this lesson, you should have learned a few things. The first one being that we can use a finite difference equation in order to determine a numerical solution for the temperature or heat transfer, the temperature of the heat transfer for a rod. Second is that our initial boundary condition and boundary conditions both affect our numerical solution very heavily. The third, that our stability relies heavily on our key parameter R, which is equivalent to the thermal diffusivity multiplied by the change in time over the change in distance squared. We also learned that there is a critical stability limit for this problem, and that can be determined or visualized using Excel, which is a great tool to not have to calculate all these numbers in order to determine what that limit is. Instead, you can just plug in numbers to Excel and let it pop out a visual explanation of how heat transfers to show you when things start to go awry and when that key parameter is no longer shows us that our numerical solution is stable.